For over 50 years, science has faced a profound mystery that challenges everything we thought we knew about gravity. In the outer reaches of galaxies, stars orbit at speeds far too high for the visible matter alone to explain. Then came the Hubble tension, two different measurements of how fast the universe is expanding, and gravitational lensing, light bending around galaxies with a strength that suggests far more mass than we can see. All of this led us to invent dark matter, an invisible substance that makes up 85% of the cosmos. But what if there is no dark matter at all? What if the darkness we see is not missing mass, but a failure in our coupling to reality itself? Take galaxy NGC 6503. Newton's law predicts that orbital speeds should decrease with distance. Yet observations show the stars continue to orbit at a constant high speed, around 120 kilometers per second, even at the very edges. This same contradiction repeats across hundreds of galaxies, in the expansion of the universe, and in the way light bends around massive structures. Something was clearly missing. In 2025, independent researcher AM proposed a revolutionary idea. The darkness we observe is not missing mass. It is a change in how we couple to matter. At the heart of the dynamic cosmic coupling model lies a single dimensionless coefficient C, defined as C equals the local baryonic density divided by the local baryonic density plus alpha times the critical density at redshift z, where alpha is approximately 5 times 10 to the power of 4 and is a universal scaling parameter. The observed quantities are then simply modified as, first, velocity in the DCCM model equals the Newtonian velocity times the square root of 1 over c. Second, the observed Hubble constant equals the true Hubble constant divided by the square root of c at redshift z. Third, the DCCM acceleration equals the Newtonian acceleration divided by c at radius r. A single idea that changes everything. The model was rigorously tested on 7 diverse galaxies, from large spirals to gas-rich dwarfs: NGC 6503, NGC 2403, NGC 3198, NGC 5055, NGC 2841, NGC 1560, and DDO 154. Across all of them, DCCM achieved outstanding accuracy. R-squared values between 0.89 and 0.95, and mean absolute errors of only 5 to 8 kilometers per second. Most remarkably, it preserved the natural wiggles in the rotation curves, the precise signatures of real gas distribution, something dark matter halos struggle to explain. In the local universe, at Z approximately 0, C approximately 0.85, producing H observed approximately 73 kilometers per second per megaparsec, matching modern measurements. In the early universe, at Z approximately 1100, C approaches 1, recovering the CMB value of 67.4 kilometers per second per megaparsec. The tension disappears naturally, no new physics required. Even in the strongest evidence for dark matter, the bullet cluster and coma cluster, DCCM explains the striking separation between the hot X-ray gas and the gravitational mass. Where baryonic density is low, C drops significantly, amplifying the effective gravitational deflection, exactly as observed. And finally, we return to the beginning. The origin of the universe was not hot, dense, and opaque. It was transparent and cold. Because matter had reached the ultimate state of absolute fluidity, a condition of perfect freedom and motion with no thermal disorder. In that primordial moment, even absolute zero becomes equivalent to infinite heat. Cold and heat meet. Order and freedom become one. The universe was transparent because the coupling coefficient C was equal to 1. Then, as the cosmos expanded and densities fell, the coupling began to weaken, and we began to see darkness, where there was only ordinary matter, but we were no longer fully coupled to it. The darkness we have been searching for was never there. It was only a hidden coupling.